Yeah, so this number, it's 54 qubits on the chip.
Mm-hmm.
You find it also in literature from other companies that have been building similar chips. And the interesting thing is that this is basically the threshold of what you can still simulate with a big supercomputer.
Uh-huh.
So if you want to simulate the behavior of a quantum chip, you can use a supercomputer. And then if you increase the number of qubits, it gets exponentially harder and harder to do this. And the boundary of what can still be done is around 54. And this is why it's so interesting, because it's kind of the last thing that you can test. And in addition to this, you can do actually lots of proof of concepts.
Mm-hmm.
So you can run molecular simulations for, let's say, small molecules with maybe 10 atoms in it. You can run optimization problems for, let's say, train schedule optimization with, let's say, tens of trains or so in it. So these are the kind of proof of concepts that you can do, and we do a lot of this together with companies where they actually create quantum readiness. So they have in-house teams which want to build up know-how, build up IP, build up processes, and for this actually they get access to our quantum computers.
And when you talk about testing and the simulation on a normal supercomputer, does it mean that while you're building quantum computers of under 54 qubits, you would basically just check its behavior with a simulation on a normal traditional computer as well?
Yes, and that's very important, because in the end it's about also trust in the technology, because let's say if we go beyond 54 qubits, we are reaching a regime which you cannot anymore verify so easily with a normal supercomputer. So it's very important that in the regime of, let's say, 520 qubits, you make sure that actually the quantum processor really behaves the way you want it to behave, because this then lets you know that actually also for the larger processors, the result is trustworthy.
That's really fascinating. And then it also means that under 54 qubits, you can experiment with different ways for this computer to kind of self-test.
Yes, exactly. And of course, some things are easier to check and some others are harder to check. And actually, this is always the elephant in the room, but one application of quantum computers is the code breaking, which is a very asymmetric problem. So the way we do it right now is that usually we multiply numbers together, and doing the reverse is very hard. But if you kind of have the answer, it's very easy to check. So if you know the numbers that you need to multiply, it's very easy to do the multiplication, but the reverse is very difficult. And this is an example where actually you can test quite easily whether the quantum computer did the right thing or the wrong thing.